All right, today we are going to continue our discussion of different kinds of tests for convergences of series. And in particular today we're going to look at two different tests, but they could both be categorized as comparison tests. We are going to take what looks like a familiar sequence, series, something we've seen before, and we know, or at least we can prove very quickly, whether it converges or diverges, as a comparison to something that's new to us. That's the basic idea. So to start with, we're going to talk about the direct comparison test. Let me get my stylus just a sec. So this is theorem 912. And it starts out with a relationship between sequences. So let's let 0 be less than or equal, sorry, not less than, equals on the next one, less than a sub n less than or equal to b sub n. And there are two facts that we actually have about these particular sequences. In particular, if we know that the summation from n equal 1 to infinity of b sub n converges. Okay, so if we know the larger sequence as a series, the larger series converges, then so does the smaller one. And what you're seeing happen there is something akin to the squeeze theorem that we did, right? We're sandwiched between 0 and something we know converges, so we have to converge. Maybe not to the same value, right? But to something in between 0 and the value of b sub n, the summation of b sub n. All right, on the flip side, if instead we know that the summation from n equal 1 to infinity of a sub n diverges, then so does the summation from n equal 1 to infinity of b sub n. Again, that should make sense. If it's bigger than something that's diverging, of course it's diverging itself. Okay? So we're going to use this test with an example. So we're going to use the direct comparison test. To determine the convergence or divergence of our series. And the series we're going to look at is the summation from n equal 2 to infinity of n squared plus 1 over n cubed minus 3n minus 2. All right, just taking a look at that. From the numerator to the denominator, comparing, those two pieces, what part of each of the numerator and denominator kind of dominate the whole thing? What's really going on? What part of this really matters? The squared and the cubed, right? So n squared over n cubed, and if I were to divide just those components, what would I have? 1 over n. And what do we know about the series from 1 to n? What is it? The sequence goes to 0, but what about the series? It diverges. It was a harmonic one, right? Okay, so we basically have the series, the summation from in this case 2 to infinity of 1 over n. That's what this really basically is. Does that make sense to everyone? So we're looking at this and we're trying to decipher which pieces of this are really important and which pieces are just really not adding a lot to what's going on. Okay? So what we'd like to do is we'd like to say that if the series from n equal 1 to infinity of 1 over n diverges, and this one does too. Our expectation is that they probably both diverge. That should be the expectation looking at this. But in order to use the direct comparison test, we actually have to have this condition be true, right? And we have to have what we are expecting is that this one right here is the 1 over n, because it's smaller and it diverges, right? That we're in step 2 basically, or part 2 of this theorem. And that the other one's going to be a larger sequence term by term, so the series itself will converge as well. So that's what we're trying to see, is if we can find that to be true specifically for the ones that we're looking at. So let's take a look. If I have n squared plus 1 over n cubed minus 3n plus 2, what happens if I make the numerator smaller? What if I remove the plus 1? Does the whole fraction become smaller or bigger?
So it's supposed to be a plus 2 or a minus 2?
Yep, it is. So sorry. I'll fix that. Thank you, Hannah. So what happens when I make the numerator smaller? What happens to the fraction? It gets smaller, right? So the inequality looks like this. I just made the fraction smaller, the numerator smaller, so I made the whole fraction smaller. And we'd really like to say that these pieces on the bottom are rather inconsequential. We know that our n values are greater than 0. So what can you tell me about negative 3n and minus 2? Are they positive numbers or negative numbers? They're negative numbers. So if I remove them, does the denominator get bigger or smaller? It gets bigger. And if the denominator gets bigger, what happens to the fraction? It gets smaller. Are you seeing how we're talking through this? Because you can't just take things away and say it gets bigger or smaller. It has to really work. And it does with these particular ones. If this said plus 3n, I probably couldn't do that, right? I wouldn't know for sure that it's getting bigger or smaller. In fact, it might actually do the opposite of what I just expected. So it really does matter what you have. In this particular case, if I take away the denominator, the two pieces, the end of the denominator, it does in fact get smaller because the denominator gets bigger. And this piece right here is now in fact the 1 over n that we were hoping for, right? This is a sub n. So we've established that we actually are able to use the direct comparison test because we've found an a sub n and a b sub n that have this relationship. What we've started with is b sub n, and we found an a sub n that's slightly smaller, and we know that the a sub n diverges, okay? So what do we write down? Well, we're going to write down something like this. We have 0. It is in fact less than 1 over n, right? Which is in fact less than n squared plus 1 over n cubed minus 3n minus 2. And we know that the summation from n equal 1 to infinity, well, 2 is where our sequence starts, so we'll just start with 2. From 2 to infinity of 1 over n diverges. Okay, I need to give myself a little bit more space, just a sec. So by the direct comparison test, and if you want, you can specify this is, it's the part 2 of that. You don't have to, but it is the part 2. The summation from n equal to infinity of n squared plus 1 over n cubed minus 3n minus 2 also diverges. Does that make sense? Yes, Ethan.
Why is it when getting rid of the negative 3, not 3 and negative 2 makes it smaller?
Because the denominator is bigger. Those are negative values, so they're affecting the denominator by a negative value. If they were positive, we couldn't make that claim. Yeah, it's because they're negative. When you make the denominator bigger, which is what we're doing, we're making the denominator bigger by removing them, you make the whole fraction smaller. Okay, here's the thing. We kind of all should get the feeling that it really shouldn't matter if we make the denominator slightly bigger or slightly smaller. This is still going to be pretty much 1 over n, right? I mean, it kind of feels almost silly to be talking about it and saying, well, the denominator is slightly bigger, so now I have this appropriate, inequality going on, because it really should just work without having to be that careful. I mean, that's the feeling that we should get by doing it, is saying, but it's pretty much the same thing. That last piece of it is so not important compared to the n cubed at the beginning. N cubed is huge compared to the 3n and the 1, right? Or the 3 and the 2. And it just shouldn't matter that much. And in reality, it really doesn't. There is another comparison test that we can use, especially if we would have had, like Ethan was noticing, if we'd had that plus in the bottom, where I couldn't have made that comparison, right? I couldn't have just said, oh, look, it did in fact get bigger, or it did in fact get smaller. So that test is called the limit comparison test. So the first one is the direct comparison test. This is the limit comparison test. This is theorem 913. And it's the limit comparison test. Generally speaking, a little bit easier to use because we don't have to worry quite so much about that bigger, smaller business. And here's how it goes. If a sub n is greater than 0 and b sub n is greater than 0, and the limit as n goes to infinity of the ratio of a sub n to b sub n is equal to some value L. L has to be finite, so it cannot be infinity, obviously. L cannot also be 0. It has to be, oops, that's supposed to say L. L is greater than 0. Then, the summation from n equal 1 to infinity of a sub n and the summation from n equal 1 to infinity of b sub n either both converge or both diverge. Whatever one of them does, the other one will do as well. Okay, so I wasn't planning to do it, but I feel like we should go back and look just real briefly at the one that I did before and see how it fits in and how we could have used it, okay, without actually writing it down. So let's just take a look back. This is what happens. This might not work because I'm just doing something I wasn't planning to do, okay? So you guys are going to forgive me if I screw it all up, right? Okay, just checking. All right, take a look at this. If I were to multiply this by 1 over n, right, or n squared, I guess, 1 over n squared. Or 1 over n cubed. That's how we've done it before. Your book uses that one. We would end up getting that well, we know it's positive, right? This would be a positive sequence, so I should make sure we're getting those conditions. This is going to be greater than 0, the sequence itself. B sub n, that is the sequence we're comparing to a sub n and b sub n, that was the 1 over n, is also a positive sequence. They're both positive. So the question is going to be whether or not my limits when I actually do the fractions are going to actually work. So if I were to take, let me erase this and do it the other way. If I were to take this sequence as a sequence, a sub n or b sub n, and I were going to divide it by this one right here. The question is, when I do that, am I going to get a value for the limit that's going to be non-zero and not infinity? Okay, so if I do, then they both will actually have the ability that since 1 over n diverges, so does this other, messy looking one that we started with. That's what we would be looking for. So we're really going to do one next, but that's what you would look for on this. You would look for the division of these two factors. So I would divide, and it really doesn't matter so much the order, but I would divide one of these, I'd divide probably the messy one, by this one. And when I divide them, I would look at their limit. Okay? So let's actually do one. It's not this one, but another one that's similar. And you can see how it would work. So similar directions to the problem before, except with limit comparison test. So we're going to use the limit comparison test. To determine convergence or divergence. Of the series. And the one that we're going to do, before we actually started, I want to make a comment, but it's n equals 6 to infinity of n cubed plus 2n plus 3 over n to the 5th plus 2n plus 4. Okay, I feel like I meant to say it just a minute ago and then I got distracted. I feel like I should give some sort of a, why does the denominator, or not denominator, but the lower limit keep changing? Like this is n equals 6. I usually write down n equal 1. The last problem had n equal 2. What's going on? There's several reasons that might be happening in a particular problem. One might be that you're trying to avoid an asymptote. Vertical asymptotes, we don't want that, right? So no vertical asymptotes going on in the middle of my problem. Another might be that you're trying to avoid the negative values of a function. So you're only wanting to look at the positive values because it meets certain criteria. So it's not like cheating. They're just getting all of the details to actually work with a with a reasonable value in the denominator or in the lower limit instead. Okay, so don't be weirded out by the fact that it's starting at 6. It's irrelevant. It's just avoiding all the messiness that might have come before that or an asymptote between there. Okay, y'all good with that? Okay. This would be, I don't care whether you call it A sub n or B sub n. Let me see, what did I write down? I called it A sub n. So when I wrote this down in my notes, I said, let's call this sequence A sub n. So I've got n cubed plus 2n plus 3 over n to the 5th plus 2n plus 14. Now, if I were trying a direct comparison test with this one, I can get rid of the extra, garbage on the numerator, right? No problem. I can make the value smaller or bigger and do that pretty nicely. But the opposite will happen with the denominator because it's all addition, right? So if I make this, if I removed the 2n and the 3 from the numerator, it would make the fraction what? Smaller. But if I remove the 2n and the 14 from the denominator, what would happen to the fraction? It would make it bigger. Do you see the problem? One piece would make it smaller, the other piece would make it bigger. So it makes it difficult for a direct comparison. Yes, David?
4 or 14?
4. Sorry. I think my plus sign got in the way of my notes. Thank you.
Can you still make a direct comparison though, because you know that 2n plus 4 is greater than 2n plus 3?
But it doesn't work that way with a fraction. So you can't always say that just by changing the numerator and denominator by the same value that it changed the fraction by the same value, or slightly more, slightly less. It doesn't always work like that. So not always can I do that.
Okay.
Yeah.
Because of the odd roots.
It's because so for example, let me see, if I did 7 over 8, and then I compared it to 8 over 9, right, I increased both of them by 1. My value actually gets bigger, like that. I mean, you have to be more careful. I mean, fractions don't have the same value. It's not like changing the numerator and changing the denominator by the same amount don't change the fraction by the same amount. Does that make sense? Or leave the fraction unchanged? Yeah. Good news is we don't need to worry about it. You ready? We know that the reality is that all of this stuff is really inconsequential, right? It doesn't really affect things in the long run. You get the n value big enough and the n cubed and the n to the 5th at the very beginning dominate everything, correct? So these pieces are rather unimportant. So the reality is that this is approximately the same in the long run as n cubed over n to the 5th, which would reduce to what? 1 over n squared. And so 1 over n squared is going to be my b sub n. Okay, so we've got two fractions. They're not exactly the same, but they're pretty close, right? 1 over n squared, is it always positive? Yes, right? I put in values for n that are positive. I'm going to get positive values over 1 over n squared. What about my original one, a sub n here? Is it always positive? Yes, I got all kinds of positives everywhere in that one, right? Yeah, so it's always positive as well. So that means that it actually satisfies these two conditions up here, correct? So let's actually say that. We checked it, it works. So a sub n is greater than 0, and b sub n is, that looks like a bn. B sub n is greater than 0. Both of those are true. Now the only other thing that we have to have true is have that limit true, right? This piece over here, I've got to figure out if that actually works. Okay, if it does, then I can use the limit comparison test. If it doesn't, then we're back to square one. So we're going to take the limit. This is what I was talking about on the last problem that we didn't actually do when we looked at this property. The limit as n goes to infinity of a sub n, and again, it doesn't really matter which one we called it. We called it the original function, so that would be n cubed plus 2n plus 3 over n to the 5th plus 2n plus 4. And I'm going to divide all of that by b sub n, which is 1 over n squared. Well, division, of course, is the same as multiplying by the reciprocal, so this would be equivalent to having the limit as n goes to infinity of n cubed plus 2n plus 3 over n to the 5th plus 2n plus 4 times n squared. So far, so good? All right. Once again, I'm out of space. Let me try to fix that. Okay, so this is going to equal the limit as n goes to infinity of n to the 5th plus 2n cubed plus 3n over n to the 5th plus 2n plus 4. All good so far?
So it's 1.
It is 1. Yeah, it is. And to show that, we can actually go back to what we did earlier on in section 1, like 9.1. Let me move this because I'm running out of space again.
Would it be 3n squared?
Yeah, but
Did I mess one up?
yeah, the plus 3 squared.
Where's my 3 in? Oh, here. You're right. I'll fix it. Yep. Okay, so what we would actually be doing then is we would dividing by 1 over n to the 5th, right? Not dividing by, multiplying by 1 over n to the 5th twice. And this would give me the limit as n goes to infinity of 1 plus 2 over n squared plus 3 over n cubed over 1 plus 2 over n to the 4th plus 4 over n to the 5th. Yeah, and they all go to 0. Lots of zeros everywhere. So there's that 1 that you saw there. So this limit is 1. So the limit as n goes to infinity of a sub n over b sub n is equal to 1. And we know that the summation from n equal 1 to infinity, well, we'll use 6 just because the problem exactly starts at 6. N equals 6 to infinity of 1 over n squared does what? What does this do? Converge or diverge? It converges. Do you remember why? Somebody thinks that it, what was it? We don't have that many rules right now. I mean, yeah, p-series test, right? It converges by the p-series test with p greater than 1. The p in this case would be 2, right? It's a power of 2. That's greater than 1, so it converges. Thus, the summation from n equals 6 to infinity of n squared plus 2n plus 3 over n to the 5th plus 2n plus 4 converges. Why? What's our new test? By the limit comparison test. The one we just did, right? And as I was doing that, I feel like maybe I should go back real quick to the earlier one we did because I want to double check. We said direct comparison test. I didn't actually state this, although we said it out loud. I just didn't write it down, that this diverged. Why did we know that the summation of 1 over n diverged? There's a couple of different things you could say.
Well, if we're doing it by p-series, it's into the 1.
Right. So we could state the p-series test. That would definitely be possible. P-series with p not greater than 1, right? What else could we say? There's another possibility. It's the harmonic series, and that would work too. So either of those would be reasons why this doesn't work. And we specifically proved the harmonic series did not work sort of as a standalone issue. Okay? All right. I told you it would be brief. I have a homework for you, but then I have something else for us to take a look at today. This is page 616. Number 4, 7, 10, 13, 16, 19. And I know this looks like long, 23 through 30, but that's what we're going to do next. I'm going to start there. So jot those down. Okay. I was going to say let's get into groups of 2, which works really evenly, except that Joseph's missed a few class periods, which doesn't seem to be fair to throw him into a group exactly like that. So I think I'm going to do groups of 3 and then 1 group of 2. So 7, 4. All right, so we're going to get to know somebody new today. I always hated when teachers did this, and now I get to do it. It's fun. All right. Yes.
Do we need to turn in 23 to 30 on Monday, or is that just
Yes.
what we do?
We're going to start with that's where I want you to start on the boards, but yes, it will still be turned in to be done. So I'm going to encourage you to get on the boards and to have your phone so that when you get done with the problem, you can just take a picture and then you can kind of put it in the right location in your homework. Because I don't know about you, but I'm kind of OCD about organization personally. And if you're not, that's fine. But, this is one of those, like, you're allowed to have your phone out in class and I'm not going to get mad at you kind of things. Okay, so we're going to count off by 4s, I think, is what we're going to do. No 5s. We'll do by 5s. So just count real quick for me.
1, 2, 3,
4, 5,
You're 1. Good.
3, 4, 5, 2, 3, 4.
Okay, so whoever's group number 5 has only 2 people, but everybody else should have 3. So raise your hand if you're in 1, if you said you're number 1. Look around for where the people are, okay? Raise your hand if you're number 2. Look around where the people are. Number 3. Shayna, you're not all these numbers. Number 3. She's not for me. Okay, number 4. And who's my group of number 5s? All right, Andrew and David. Okay, all right, hop up, find a board space. This is like an amazing room for board space. If you need some chocolate, looks like there's a couple boxes over here. Feel free to grab some. You're taking a look at the questions 23 through 30. And I will pull them up on the screen too if you don't